Today we're going to talk about mixtures and solutions. First, I'd like you to watch this video.
The world we live in is made of things. Billions and billions of different things like pickles and pianos and dump trucks and octopi. And even though these things seem totally different, they're all made of the same stuff, just combined in different ways. To give you an idea of how this combining works, let's take something apart. Let's start with this bowl of macaroni salad. If you were to reverse a recipe for macaroni salad, you'll see it's made by mixing together a bunch of ingredients, like macaroni, mayo, vinegar, vegetables, and mustard. This type of combining is called a mixture. When you make a mixture, you're combining two or more things together without actually changing the chemical identity of those things. Like mud, for example. The soil and water in mud haven't actually changed. They're still soil and water. You've just created a mixture of soil and water. Mud. It turns out that macaroni salad is actually a mixture of mixtures, because many of the ingredients, like mayo and mustard, are already mixtures themselves, which is nice for us because if we look closely, we'll see the three main types of mixtures that exist. The size of the particles in a mixture determines the type of mixture. On one end of the scale is a suspension, like our muddy water example. You get this if you take big chunks of something and mix it with something else, so those chunks are just floating around. Take runny mustard, for example. You'll see a bunch of little particles like mustard seeds, pepper, allspice, and minced shallots all floating around in a liquid, in this case, vinegar and water. This is called a suspension because you've got particles of one thing suspended in another. Now, on the other end of the spectrum is a solution. The particles in this mixture are so small, they are the actual molecules. A solution is sort of like a suspension of molecules, where one type of molecule is blended or dissolved with another. Vinegar is an example of a solution where the molecules of acetic acid are blended with molecules of water. The chemical properties of the molecules haven't changed, they're just evenly mixed together now. Salt water and carbonated soda are both examples of solutions where other molecules are dissolved in water. The last type of mixture is called a colloid, which is somewhere between a suspension and a solution. It's when you take two materials that don't dissolve and you make the particles so small that they can't separate. Mayo is what happens when you take oil and water, which don't mix, and you bind them together, usually with the help of another substance called an emulsifier. In the case of mayo, it's lecithin found in eggs. And now you're left with really small globs of oil hanging out with really small droplets of water. Whipped cream, hairspray, styrofoam, and jello are all other examples of colloids. So, let's get back to macaroni salad. You've got colloids like mayo, suspensions like mustard, and solutions like vinegar. But you've also got celery, shallots, and all other vegetable chunks that are also part of the salad. These aren't mixtures really, but we can break them up. Just like a TV can be broken up into smaller and smaller complex component parts. In the case of vegetables, if you keep breaking things up, you'll eventually end with thousands of complex organic molecules. Things like ATP synthase and RNA transcriptase and water. So now, once we've unblended all the solutions, unmixed all the colloids, separated all the suspensions, and taken apart all of our vegetables, we've reached the end of what we can unmix physically. What we're left with is a whole bunch of molecules, and these molecules remain chemically the same, whether they are by themselves or thrown together in a salad. If you want to separate these guys even further, we need to unmix things chemically, which means we need to start breaking some bonds.
Okay, so as you see, there are lots of different types of mixtures. We're going to be focusing most of this unit on solutions. And if you'll recall, a solution is where the actual molecules are hanging out inside of the solvent. So a solution is a type of aqueous mixture. Solutions are mixtures in which water, the solvent, breaks apart the substance. We call this the solute, okay? Solutions are transparent. Now, I mentioned that water here is the solvent. You can have things other than water be the solvent, but 99.9% of the time, it's going to be water. A solution is a homogeneous mixture, which means it's the same throughout. The solute is the substance being dissolved, and the solvent is what that substance is dissolved in. So in the case of salt water, salt is the solute and water is the solvent. And it's homogeneous because it doesn't matter whether you take it from the bottom of the beaker or the top of the beaker, it's going to be exactly the same. Solutions have some important words that can get really confusing because they sound similar, so I want to make sure we go over those. Soluble means that something is capable of being dissolved. So, for example, sugar is soluble in water, which means sugar can dissolve in water. Insoluble means that things are not capable of being dissolved. For example, fat or oil does not dissolve in water. Sand does not dissolve in water. Solutions aren't always a solid in a liquid. We often think of them this way because this is how we experience them most in chemistry class. In Chem 1, we took copper chloride, which is blue, and we dissolved it in water. But solutions can also be gases dissolved in gases, or even solids dissolved in solids. Here's an example of that. An alloy is a partial or complete solid solution of one or more elements in a metallic matrix. In other words, think about it this way. Metal is a solid at room temperature, but at some point, it's not a solid anymore. So it would be a solution. It would be liquid, but we experience them as solids. So alloys are a mix of metals, and they are a solid solution. Copper and zinc make brass, copper and tin make bronze, and carbon and iron make steel. Colloids, you saw in the video, they have small solid particles. They're suspended and they're so light that they do not settle out. A great example of this is milk. Milk, you will notice on the label, often says that it's homogenized. This is because colloids are homogeneous. They're the same throughout. If you were to get milk straight out of the cow and not from the grocery store, it would not be homogenized. In fact, it would separate out. You'd get like a fatty layer, and then you'd get watery layers, and then chunks in it, and you'd have to shake it up before you drank it. But the milk we get from the grocery store has been homogenized. It means that all of the particles are teeny tiny, and they stay suspended, and they never ever settle out. Colloids are considered cloudy. They exhibit something called the Tyndall effect. The Tyndall effect is this right here. It's when the light shines through the colloid and it reflects things. Another example of the Tyndall effect is on a beautiful sunny day. If you have a dusty room, you can see that dust reflecting those particles. That's because the dust is like a colloid. Suspensions are mixtures that contain large solid particles, also in the video. They're heavy enough to settle out, like muddy water or oil and water. They're cloudy or opaque, and they are definitely heterogeneous. They are not the same throughout. So you can pull from the top, and it will be different than when you pull from the bottom. Mixtures with suspended solids, like I mentioned before, colloids and suspensions, go through something called the Tyndall effect. They reflect or scatter light. And this is just a cool test. If you have two containers, they might look identical to each other, but if you put them in a dark room and one you see a reflection of light, you can tell that that's actually a colloid instead of a solution. So let's just talk about now solutions and concentration. You've probably heard the word concentration before. You've probably heard that things can be more concentrated. I always like to bring up the example of Kool-Aid, right? You can make a really, really dark Kool-Aid with lots of Kool-Aid mix in it, and that will have a higher concentration than, say, like a lighter Kool-Aid. Anyways, the official word for this is solubility. Solubility measures the maximum amount of solute that can be dissolved in a solvent. And we measure this in chemistry, and it actually has a unit. It's in grams of solute per 100 grams of solvent. And solubility varies with temperature. You may have experienced this as well. If you were to put sugar into hot tea, it dissolves pretty easily. But if you put sugar into cold tea, it takes a while to dissolve. Most substances have a higher solubility as temperature increases. And we're going to see this on a graph in a second. But there are lots of factors that can affect solubility. For example, the particle size, right? So sugar cubes or big hunks of sugar dissolve more slowly than just plain old sugar or really tiny pieces of sugar. The temperature, like I just mentioned, higher temperatures usually hold more solute. If you stir it, or shake it, what it does is it puts energy into the solution, which helps to overcome those chemical bonds and break them apart. So stirring can affect solubility. The concentration of the solute. This one is a little bit tricky to imagine. It just means that if you try to dissolve salt in already salty water, it's not going to hold as much salt. Another great example of that is it's hard to dissolve sugar in Caro syrup. And then, of course, the nature of the solvent and solute. We studied this in Chem 1 as well. Like dissolves like. If you have substances that are alike, like polar dissolves in polar, and nonpolar dissolves in nonpolar. But if you try to put polar and nonpolar together, they're not going to dissolve. That is why spicy things stay in your mouth when you drink water, because capsaicin is a polar molecule. Capsaicin is a non-polar molecule. And so in order to get that to dissolve in your mouth, you're going to have to put other fatty molecules in there, like milk, because water is polar. And so water will not dissolve non-polar capsaicin. So like dissolves like means that nonpolar dissolves in nonpolar and polar dissolves in polar. And of course, there's some gray area here. You can have things that are slightly polar that dissolve in other slightly polar things. Or maybe if it's slightly polar, it'll still dissolve in a nonpolar substance. This is not black and white. You can make some predictions using your knowledge of chemistry and the periodic table, but you're not always going to get it right. Some more solubility terms for you. Saturated. Saturated means that the solvent has dissolved the maximum amount of solute possible. Any more solute added will not dissolve. This is like saturated like a sponge. Like a sponge is saturated with water, right? Unsaturated means the solvent can still dissolve more solute. It can hold more. It's an unsaturated sponge. That solvent can hold more solute. And then supersaturated, this is kind of a funky one. This means that more solute is dissolved than the solvent should be able to hold. This is a very special case and only happens with certain chemicals under certain conditions. Okay, here's an example of an unsaturated solution. There's nothing on the bottom, more solute can dissolve. A saturated solution means that no more solute dissolves. If you drop it in, it'll just fall to the bottom. If a solution is saturated and you drop 5 grams of solute into the solvent, 5 grams of solute are going to settle down at the bottom. And then a supersaturated solution means that you have done something to make it overly saturated. This often happens when you make it really hot, you dissolve the solute in it, and then you leave it on a counter and it stays, it kind of comes out of solution. This is really hard to describe because it's not something that we see every day. Here's an example of a supersaturated solution using a special chemical called sodium acetate.
The flask contains a supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution. Focus your attention on the portion of the solution to which the crystal is added.
And it's actually getting hard and it's getting hot and it's actually crystallizing instantaneously. It's pretty cool actually to see.
Here is the process again in slow motion.
There's that little tiny drop. It falls into this supersaturated solution and the crystals form throughout it. So in other words, it was holding more solute than it should have been holding. Again, this doesn't happen with all chemicals, kind of a special thing that we don't encounter every day. So let's take a look at solubility curves. Solubility curves are just reading a graph. This may look really complicated because there are lots of curves to see here, but it's really not that complicated. You're only looking at one curve at a time. A solubility curve has temperature at the bottom because we talked about how when things get hotter, they hold more solute, and then has grams of solute per 100 grams of water. Now, why did they use 100 grams of water? Well, they had to use something. You can transfer things to 50 grams of water by cutting this in half, but they had to use some amount to show solubility. I want to take a minute to read these solubility curves. They're pretty easy. Questions might come up like, if the temperature is 30 degrees Celsius, how much KCl will dissolve in 100 grams of water? So you go to 30 degrees Celsius, you go up, you find KCl, and then you work your way over and you find out that, I don't know, maybe about 36 grams of KCl will dissolve in 30 degrees. And 36 grams in 100 grams of water. So there's lots of different ways that you can read these. On the line is where it's saturated. If there's anything under the line, like say for example, it's 30 degrees and you put 20 grams of KNO3 into 100 grams of water. Well, it's going to be unsaturated. It's going to be below this line right here, unsaturated. In order for you to saturate it, you would have to add this much more. So, about 27 more grams in order for it to be saturated on that KNO3 line. So just take your time to read these graphs. Above the line is saturated unless it's a very special case and it says something about supersaturated. But most of the time with these chemicals that we have here, if we read above the line, we consider that simply saturated and the chemicals are going to be found sitting on the bottom of the container undissolved. So if you take a look at the graph, you're going to see that gases are more soluble at low temperatures. This is opposite, right? So back to this graph, look at these right here. NH3 is a gas, ammonia. Ammonia solubility goes down as it gets warmer. Gases are also more soluble at high pressures. We call this Henry's law. Henry's law says the higher the pressure of a gas above the liquid, the more the gas will dissolve. Examples of this would be like soda. If you have it under high pressure, like if you have pressurized soda, it's going to hold more CO2 gas in it. The same goes for when your pop is cold. When the temperatures are low, it holds more gas.